Okay. Okay. All right. So in this lesson, learn about new rules for computing derivatives. We've seen a few rules already. The power rule that you've used most often for handling x raised to a power. Um, Also, the sum and difference rules. So if you have several functions added together, then you can take the derivatives of those functions individually and then add a result. So in other words, the derivative of a sum is a sum of the derivatives. But it's very important to keep in mind that that does not apply when functions are combined in other ways. So adding, subtracting, those cases are easy. But here we have a case of a function f of x being a product of two functions or a quotient. So here we have rules to obtain the derivatives in those cases. So uh, so in this lesson, literally, you're going to have to mind your P's and Q's. So if we have f is equal to some function p times some function q, if you can recognize it as such a product, then by the product rule, this is a derivative. Notice that you have two terms, one involving p and one involving q, involving both p and q, and in each term, one function and only one of them is being differentiated. So here we have q times p prime. Here we have p times q prime. A lot of times students will make mistakes, like they'll differentiate the wrong function, or they might have both p prime and q prime in the same term. Remember, here you differentiate one of the two functions, and then you're putting a shoe on the other foot for the other term. So that's the product rule. The quotient rule, so if you have f is equal to p divided by q, is somewhat similar. Notice the numerator in the result is very similar to what the product rule gives you, but instead of a plus here, we have a minus. So it's q p prime minus p q prime. And then whatever your original denominator was, that gets squared in the denominator of the derivative. So these are the rules that must be applied whenever you differentiate a product or quotient. Okay. Now, because these are more complicated formulas for derivatives than what we've seen before, what I would strongly recommend is that when you're given a function that is a product or quotient and you need to take a derivative, identify the pieces, p and q, and go ahead and write them separately. And then take the derivatives of each one individually, because you notice both formulas involve p, q, p prime, q prime. So go ahead and get your ducks in a row before you work on a derivative of the original function. Just have these things in front of you, like written off to the side or something. And then once you have those four pieces, you just put them together according to these formulas. So if you break it down like that, first get your individual pieces, your ingredients, and then put them together. That can help reduce mistakes. All right. So since I referred to this when presenting this originally as getting your ducks in a row, then these four pieces are referred to throughout as your ducks. Okay. So here we have for our first problem, we have a function that is clearly a product since it's factored as such. So we're going to use the product rule. So the first function in the product is the p, and then the second function is the q. So we go ahead and make a note of those. So p is this, q is this. Then we take the derivatives of those individual pieces. So here with 5x squared plus 7, we take a derivative of that. The 7 won't give us anything. It's a constant. So then we use the power rule on the 5x squared. So we get 5 times 2 times x. So we have 10x. And then over here, minus x minus 4. We just use a coefficient rule. So a derivative of minus x is minus 1. So now we have our ducks in a row. We have our p, q, p prime, q prime. So then we just go ahead and put those together. And if you write them out this way, p, q, p prime, q prime. So if you're following my convention and how I lay out this information, then what we see here is for a derivative, I end up taking the two terms in the middle, so q and p prime, multiply those, plus, and then I have the outer pieces, so 5x squared plus 7, and then times minus 1. So now I have a derivative. After that, I just do a little cleanup. So I go ahead and distribute, and then generally this will lead to some like terms that can be combined, and this is the final answer. Although in Hawks, I would not recommend taking a lot of time to try to simplify answers. Generally, Hawks will still recognize it as a correct answer, even though unsimplified. If you feel that you really did have a right answer and Hawks marks it incorrect, on one of these homework assignments, please let me know, because I can go ahead and review it and override the score. For tests, I review all problems on a test anyway. Can either give partial or full credit if you give the answer that really is correct, and for some reason Hawks marks it wrong. It does happen on occasion. Okay. This problem underscores the fact that to get a derivative of a product at any point, so in this case, we want a derivative at x equal 5, all we need are, if h is a product, we need the values of these functions at x equals 5, and also their derivatives at x equals 5. So here I have h is equal to f times g, so f is playing a role of p and g is playing a role of q here. So here we have gf prime plus fg prime. Again, in each term, only one function is differentiated. The other must be left alone. So now I plug in x equal 5 throughout, and now I can just take the numbers that I'm given and put them in here. So g of 5 is minus 4, f prime of 5 is minus 11, and so forth, and then just go ahead and combine everything to get the result. Okay. Another product rule 1. So here we have f is a product of these two functions. So we pick out, here's our p, and here's our q, and then take a derivatives of those. So again, we're using the power rule in both cases to get, so minus 6x squared gives us minus 6 times 2 times x, so that's minus 12x. And then here we have minus 7 times 3, and then times x squared, so thus we get minus 21x squared. So now we have our ducks in a row. Let's go ahead and put the derivative together. So we have the two terms in the two items in the middle. Give us our first term plus these two on the outside. Go down here, and then we go ahead and multiply everything out. So we distribute through here, and we see that we have two like terms involving x to the 4th, so 84 plus 126 gives us 210. And there we have our derivative in the simplified form. Now, the process is much the same when we have a quotient and you're using a quotient rule, but how you set it up is the same as for products. You need the same information. So here the numerator, minus 3x to the 4th minus 2, that is our p. Denominator 2x squared plus 2, that is our q. So again, using a power rule, we take the derivatives of these individual pieces. The constants give us nothing, so we get the power rule to get these derivatives here. And then, again, we put them together. So q times p prime, the 2 in the middle give us this, minus this time, because it's a quotient rule, The 2 on the outside get multiplied, and that gives us our second term, over the denominator squared. Now, do not take time to multiply out the denominator. Just leave it in this form where it's some quantity squared. All right. And then in the numerator, we go ahead and simplify that as well, combining any like terms that we get. All right. All right. Now that we've seen some examples, let's see. Okay. Involving the product and quotient rule. Are there any questions up to this point? Okay. So this, actually, we'll take a look at the problems that are coming up. Okay. All right. Okay, this is one I just did. So here too, here's our P, here's our Q. So this process, it really is very similar to the other examples from above, where we have power rule to get the derivative of P and then the derivative of Q. And then, once again, two items in the middle give us our first term from a product rule. Ones on the outside give the last term. Now, I want to emphasize, I'm writing these out in a consistent manner just so that I can put them together consistently too. But make sure you write them in the same order in which I did: P, Q, P prime, Q prime. If you want to go ahead and follow this approach that I'm doing here, again, that's a personal preference thing. But it just works out because I wrote it this way that you put these terms here, these here. Okay. And then we go ahead and distribute. So here we have x squared times x to the fourth is you add the exponents, that's x to the sixth. And then we once again have some like terms to combine. Now, this is not the only way to do this problem. And I want to point it out here. Okay, after the solution. Okay. Because what I could have done is rewritten f of x by taking this x squared and distributing it through here. So I have minus 7x to the 7th, and then minus 7x squared. So then I could take a derivative in the usual way using a power rule. So I have minus 7 times 7 is minus 49 x to the 6th minus 7 times 2, 14 x. And of course, it would agree with this result. Now, I'm pointing this out because once in a while, it's feasible to do this and just work out derivative that way, thus avoiding a product rule. Now, the problem may say use the product rule or quotient rule to find a derivative, but what you input into Hawks is only the final answer. If you worked out the derivative another way, like this, and it's correct, then there's no distinction as far as Hawks is concerned. Some sites, some homework sites would have you enter intermediate steps, so you'd have to carry it out this way. But Hawks isn't doing that. So I want to keep that in mind. If you see a case like this where you could just go ahead and, if you would prefer to do it this way, there's really nothing to stop you. On the flip side, though, if you have a function that's much more complicated like this, and there will be some as we go through the semester, where multiplying it out would also be quite unpleasant, in that case, you might as well deal with a product rule after all. So for cases like that, it's up to you. But I generally do not begrudge students using alternative approaches to solve a problem if you're still gonna get the correct answer and the reasoning is sound. Okay. Here another one with the quotient rule. So P is our numerator, Q is our denominator, and then we take the derivatives of those individually. Again, the power rule is all that is called for in doing that. So then we once again put our pieces together. So middle one's here minus the product of these going down here, and then multiplying it out. And in this case, we once again had two terms that could be combined. Okay. Here we have a function of t, so we're going to have, keep in mind your variable. I've seen it happen sometimes where, okay, we see most of these problems, you're given a function of x, but once in a while you're given a function of a different variable like t, or maybe even sometimes a different letter, and you must stick with that letter, whatever letter is given in the problem. Now, on a test, for example, if it gives you a function of t and just out of habit you work with x, but you otherwise get the right answer, I will go ahead and give you credit for that. But to make things easier on everyone, pay attention to which letter is being used for a variable, because oftentimes they have different meanings. T is generally used to refer to time, x to a point in space. Okay, so here we have, check what's going on here. Okay, I'm trying to make sure I don't miss anything in the chat or whatever. Okay, so here we have our numerator minus 5t, denominator 8t plus 5. So then these are both linear functions, so they turn out to be constants for the derivative. So that makes things a little easier. And what we have here is then we go ahead and put the pieces together the same way as in previous problems, according to the quotient rule. And then when things are multiplied out and combined like before, we have these two terms canceling, and we're left with just a minus 25. Now, one thing I'm going to point out, and I'm not really going to take the time to go through it here because it's not actually part of the lesson, but here, when I presented this yesterday, I worked out the problem in a different way, because my original function up here, I have multiple of t. And it turns out if I can make these be the same multiple of t, same constant up front, I could find a way to simplify the function for the purpose of taking a derivative. So what I did here was I multiplied and divided by 8. And I took the minus 5 in the original function and just put it off to the side. So multiplying and dividing by 8, that gives me an 8t up front to match with the 8t down below. And then I did a add subtract trick. I had 8t plus 5 down below. So up above, I added 5, but also subtracted 5. That let me get these two fractions, and now we have the numerator denominator matching. So this simplifies to 1. So then when I'm taking a derivative of this, I'm going to get 0 here. So here I go ahead and take the derivative, and of course wind up with the same result. But I wanted to show this anyway, just because there are certain common tactics that you can use, certain algebraic maneuvers to rewrite a function in a form that might be easier to work with. Because here in the original function, I had these constants not matching. Well, I wanted an 8 there. Well, fine, put an 8 there, as long as you divide by it. Here I wanted a plus 5 here. Fine, go ahead, put it in, as long as you compensate for it. So often it's useful to get a function into a different and possibly more preferable form. Okay. what I realized in the process of working this out, this is a differentiation rule that'll be from an upcoming lesson, actually the very next lesson, 3.2. Here's a familiar power rule for handling x to the n. But what if you have something slightly different? Here I have ax plus b all raised to the nth power, where a and b are constants. It works out much the same. You still have n coming down. You still have your original expression raised to the n minus 1 power. The difference is, because a is multiplying x inside, you must have a here multiplying it outside. But we're going to see more of that in the next lesson. Okay. Here we have a problem involving fractional exponents. So a new wrinkle here. So here we have our p, and here our q. So then we have our pieces. And then to get the rest of our ducks in a row, we go ahead and take the derivatives of these. So for this one, the minus 6 we can ignore, it's a constant. So we have minus 3 times 1/3 coming down, and then x to the 1/3 minus 1. Now the 3's will cancel, and you'll get minus x, and then we subtract these exponents. Well, 1/3 minus 1, that's the same as 1/3 minus 3 over 3, so that's minus 2/3. This one works out the same way. We just have a different constant up front. So we have 2 times 1/3, and then again x to the minus 2/3. All right, so keep in mind how we handle these fractional exponents. And when you're subtracting 1, after a while you get a habit where you can just say, oh yeah, 1/3 minus 1, that's minus 2/3. Until you get used to that, it's a good idea to write it as a using a common denominator, like I will show you there. So then we just subtract the numerators. Okay, now that we have our ducks in a row, we go ahead and put our pieces together. So the middle 2 go here, minus the outer 2 going here, and then denominator squared. Then to simplify this, we need to use law of exponents. Here we have x to the 1/3, x to the minus 2/3. So we add the exponents because we're multiplying them. So we have 1 minus 2 is minus 1/3. So that's this first term here. And then the same thing happens over here. What was done was here I have a common factor of minus 3. So I factored that out. And then from here I have a 2/3 already. This 2/3 times this 3, the 3's cancel. So I end up with a minus 2 out here. That's where that comes from. And then I take this x to the minus, then I take this minus 2 and distribute it through here. And then I'll distribute the x to the minus 2/3 through all this, again, using the laws of exponents to add the exponents. And we see we have these terms end up canceling, and then the other 2 terms end up combining, and that's our final result. Alternatively, what I could have just done was just taken this and distributed through there right away, and that would have taken me directly to this point. All right. Okay, first word problem of a bunch. So here we have a function that models the population over time, where t is in years, the population is in thousands. And here a function involves a product. So what the question is asking is, how fast will the population be growing? So it's asking about a rate of growth. That's derivative, because what is a derivative? It's a rate of change. In this case, it's rate of change of the population with respect to time. So we need the derivative of this function. Now, when we take the derivative, the 85 won't give us anything, and derivative of that will be 0. So we're just going to focus on this, for which we need the product rule. So here we, again, get our ducks in a row, our p and our q, and then the derivatives will just be the coefficients of t in these cases, because these are linear functions. So there are 0.2 and 0.9 there. And then we put them together the same way, these two multiplied together, plus these two multiplied together. And then we go ahead and expand, and we see that these terms cancel, these two combine, and we get 0.36t as our derivative. Alternatively, you could have multiplied this out at the start, and then you don't need the product rule, you can get the derivative that way. Okay, so then, all right, but that's for the rate of growth of population in 6 years. So we need to plug in t equals 6, and this is what we get. Now, in this case, it says round your answer to 2 decimal places. This is the exact result. It already has 2 decimal places, so there's no need to round this case. But in general, remember, as I said before, keep around more decimal places than you need. Generally, you'll be asked for 2 decimal places. Don't round it to 2 decimal places until the very end. Okay. Here, there's actually no difference in this product, this quotient rule example, than with previous ones. So in terms of problem-solving technique, it doesn't really offer anything new. It's the same kind of function as before, whereas there are more, shall we say, interesting problems that follow. So I'm going to skip this one, but at least you have it written up. Okay, here we have another word problem. We have a cost function given here, and the problem asks for marginal cost at a certain value of x. Marginal cost, remember from a previous lesson, 2.4, is the derivative of cost. So here's our cost function again. When we take the derivative, this will not contribute anything, so we're going to focus on this product. So here we have, actually the two factors happen to be the same. So p, q are equal, therefore p prime and q prime are equal. So then, oh wait, sorry, they're not exactly the same. 80 here, 30 here, but the derivatives are the same. All right. So we have our ducks in a row. So then we have our middle 2 factors go here, plus these 2 factors going here. So q p prime plus p q prime. Then, as usual, multiply it out, combine any like terms that we have, and then we substitute in x equals 87 to get the marginal cost at that number of items. So when I've carried this out, I'll do this on the calculator. Your calculator, of course, will give you more decimal places. So this is what we have to 4 decimal places, which is a good guideline. We round to the nearest cent. So 2 decimal places, that'd be 82.09 for the result that you would actually enter into hogs. Here's another example that calls a material from a previous lesson. We have a demand function for a particular item, and that's for marginal revenue. Now, as you've seen before, marginal is code for a derivative of revenue. But we don't have revenue, we have demand. So we need a function for revenue. Now, demand, you can also think of as the price at which this item will sell. So to get to revenue, we take the price per item times the number of items. So that would be the total revenue. So revenue R of x is x times d of x. So we go ahead and fill in what the demand function is. And this fraction is our revenue function. So that's what we're going to take the derivative of to get our marginal revenue. So this is going to call for the quotient rule. So here, our numerators are P, our denominators are Q. Take the derivatives of those. In this case, the coefficient rule is all that's needed to get those derivatives. And then we have a quotient rule. So Q P prime here minus P Q prime down here. And when we multiply this out, we have 158 times 2 times x, and here too, 158 times 2 times x. Those are going to cancel. And what's left is 5 times 158, which is 790. So now we have our marginal revenue function, and it asks for the marginal revenue when x is equal to 6. So we go ahead and plug in x equals 6 and work that out. We do need to round to 2 decimal places. We're rounding to the nearest cent. So 2 decimal places, and this is what we get. Okay. Here, we're doing something different with a derivative. Here's our function, and that's for the point on the graph of this function where the slope of a tangent line is equal to 6. Now, the slope of a tangent line, that is the derivative. So if we have a tangent line at some point, x naught, the derivative evaluated at x naught is the slope. So we need to solve this equation. We need to find a value of x naught so that the derivative at that point equals 6. So first we need a derivative. So here we proceed with the product rule as before. Just using a coefficient rule gives us derivatives of our 2 factors, P and Q. We put them together as in several other examples, and then simplify as best we can. So our derivative turns out to be minus 20x plus 2. Honestly, if I had to get a derivative of this, I would just multiply this out because that wouldn't take much to do, and then take a derivative that way. But again, it's a personal preference thing. Hawks is not going to know or care. So now we want to find when this derivative, this is the slope of a tangent line at whatever x. So we set this equal to 6. So now we have this equation that we solve for x. So here I move a 2 to the other side. And then when I divide, I'm going to get x equal to minus 1/5. So that is the x value where the slope of a tangent line is 6. But if we go back to the original question, find the xy coordinate on the graph where the slope is 6. We have the x coordinate. Now we need y. To get that, we take our x value of minus 1/5 and we substitute it into the original function, not the derivative, the original function. And that's what's done down here. So f, not f prime, f at minus 1/5. And we work all that out and get 36 over 5. So described as an ordered pair, these are the x and y coordinates of that one point on the graph of f where the tangent line has a slope of 6. Okay. Oh, okay. I just realized that when I was presenting these yesterday, I ran out of time. But okay, I have. Okay, I have those spelled out. But okay, I do have these worked out. I also realized that in the notes I posted yesterday, these problems were not included. So I will repost the notes so that you have everything. Okay, so this is a strange one involving the quotient rule. Okay. Okay. This is odd. Okay. All right, I'm going to have to change the way this is written up, but okay. I want to carry out the same way as before. So numerator, 6x to the fifth plus 14x squared minus 15x cubed minus 35. Okay. Q, the denominator, minus 3x cubed minus 7. Okay. And then, because these are long, I'm going to have to write the derivatives below them. So here I have power rule, 30x to the fourth plus 28x minus 45x squared. If it minus 35 gives us nothing. Then q prime, so that'd be minus 9x squared is all we have here. Okay, now what does the quotient rule call for? So it is q p prime. I'm going to fill it in down there the way it's written. I've written it up here. Okay. Okay. So here I have q p prime goes first minus p q prime. So now what you can do is go ahead and multiply this out. This is going to be quite the exercise to do that, which I won't carry out here. But what you get in the end is this. Now you can stop here. This is the derivative. But what's interesting about this problem is, first we have a common factor. I'm going to throw in an intermediate step here. Okay. This numerator has a common factor of minus 4x. So I'm going to factor that out. So after dividing by minus 4x, I'm going to get 9x to the 6. And then I get 42x cubed. Whoops. Okay, and that'll also be a plus because I'm dividing by minus 4. And then 196, it's 49 with no x. Okay. Now, this actually turns out, now, this is not something I would expect you to recognize. But this turns out to be a perfect square. This is 3x cubed plus 7, the whole thing squared. And here, inside, in the denominator, I can factor out a minus 1 squared. And we have that. So those cancel. And the derivative turns out to be minus 4x. That's not something you would be required to simplify to get to that point, but I'm just pointing this out. If you're working through one of these, and then you have, like, say you're not able to get it, and then Hawk shows the answer, and you wonder how did it get to be so simple from such a complicated function, it's because it's something that factored in a nice way. Now, another way to have see this can actually be factored by grouping, a technique you may recall from Math 101. That would end up simplifying the function as a whole, and then from there it would be easy to see that the derivative is minus 4x. So sometimes that happens where things factor out nicely, but again, I would not expect you to recognize that that is a perfect square and therefore can be simplified in this manner. So something like this is perfectly fine as an answer. Okay. Look, I have some formatting error here. I can't tell where it is. Okay. No. Oh, here. All right. Now here we have another product rule example. So all right, so P of U, this is a function of U, so that's 2 plus 1 over U. But I'm going to write it this way, 2 plus U raised to a minus 1, because I need to take its derivative, and it's easier to do it in that form. Q is U cubed minus 1/7. P prime, take a derivative of this, the 2 will give us nothing. But here we have minus U to the minus 2. So that would be minus 1 over U squared, written as a fraction again. And then Q prime, from here, that'll just give us 3U squared. Okay, so now we go ahead and put everything together. All right, so this times this plus this times this, and then when we go ahead and simplify, we need some laws of exponents. Here we distribute the minus 1 over U squared through here. We have U cubed over U squared, so that gives us a U with the minus. And then here we just multiply these fractions. Here we have 6U squared, and then we have U squared over U would be U. Okay. So then we now what's done here is I'm going to also add a intermediate step. Okay. See how you get from one to the other. Okay. Because here we have a denominator of 7U squared, but and there's no other term of a denominator. I'm going to combine like terms too. So I have okay, 6U squared, and then these terms combine to be plus 2U. Sorry, that should be a 6, not a 7. Okay, and then I have this last term of plus 1 over 7U squared. Okay, but now what I'm going to do is I'm going to take this part that doesn't have that denominator and multiply and divide by the denominator of the other term, 7U squared. That way I can have everything over a common denominator of 7U squared. So I have 6 times 7, 42U to the 4th, add the exponents, plus 14, 2 times 7, U cubed. So that's where this fraction comes from. Although, sorry, I actually have one of my graduate assistants running this up. So then I simplified and got back to this answer. Sorry about that. I should have scrolled down further, but either this form or this form is perfectly acceptable as an answer. All right, so actually probably the best thing to do is jumping directly from here to here. Okay. Again, I apologize for any confusion I caused. Again, I do not care how these are simplified, or even if they're simplified. What matters is that they're correct. All right. Here, product rule called for again. So get our ducks in a row. P of u is the first factor. And I'm going to write it as 4 times u to the minus 3. So that's better for taking a derivative. Just use a power rule right away. Q of u, the other factor, is u cubed plus 3u minus 9. Then take the derivatives. So p prime will be equal to minus 12 u to the minus 4. But that's the same as minus 12 over u to the 4th. So you can write it either way. And then finally, q prime of u is 3u squared plus 3, using the power rule and also the sum rule, taking derivatives of these individually. Okay, so now putting it all together, so this times this plus this times this, again written as a fraction. Okay. Right. I'm just going to try to simplify our presentation a little bit. So here, just written in this form, it's actually best not to write these as a fraction right away, because we're going to do some multiplying out. And what you can do is whatever exponents you have, positive or negative, you can go ahead and add them. So here, like when I'm multiplying this one out, I'm distributing a minus 12 u to the minus 4 through here. And okay. So like here I have minus 12 u to the 3 minus 4, which would be minus 1. And then here I have okay, 3 times minus 12, minus 36 u to the 1 minus 4, so that's u to the minus 3. Okay, and then and then I have minus 9 times minus 12 is plus 108 u to the minus 4. Okay. And then okay, actually this term please bear with me for a moment. Just want to have everything in its proper place. Okay. When I'm multiplying this out, 5 times 3, 15 u squared. Okay. Then we have 5 times 3 gives us 15. 12 u to the minus 1 because it's minus 3 plus 2. And then here I have 12 u to the minus 3. So here are all the terms that we get from multiplying everything out. And then we look for any terms that can be combined. So here we have minus 12 u to the minus 1 plus 12 u to the minus 1. So these two terms will actually cancel. And then we have, okay, 15 goes here, 15u squared goes here, this term goes here, and then I have two terms involving u to the minus 3. So those are like terms that can be combined. It gives you minus 24 u to the minus 3. Okay, last problems. Find the equation of a tangent line. So you still need a derivative, you just have something a little extra to do after that. Okay. So here we have our function, and we want a tangent line at this point. X is -1, y is -15. So here, same thing, getting our ducks in a row, P and Q, and then their derivatives, and then putting them together. So these two form a first term, plus these two multiplied together give us a second term. Now what we need is a derivative at x equal -1. So I didn't bother multiplying this out. Just go ahead and plug in -1 right away. That's what happens from doing all this. And then you end up with these factors and get a result of -24. So -24 is the slope of a tangent line. Now, problem asks for the equation of a tangent line. So it's easiest to use point slope form. So y minus the y value of -15 equals -24, which is the slope, x minus -1. So it's y minus the y value over here, x minus the x value of -1 over here. That is times the slope. Now we simplify. So y plus 15, we have x plus 1, multiply it out, move the 15 to the other side, and then combine what you can. And here is the equation of the tangent line. One more. Same type of problem, but involving the quotient rule. So here's our numerator p of x, our denominator q of x. And then we have the derivatives of those pieces over here. And then we have q p prime minus p q prime. And then we go ahead and multiply this out and combine any like terms that we have, because we're going to have 7 terms altogether, but we're able to do some combination to get this right here. Now, once we have a derivative, we need the slope of a tangent line at x equal 2. So the x value is substituted in, and the result is the slope of our tangent line. So again, we do the point slope form. So the y value is -3/2. So I have y minus the y value is the slope times x minus the x value. So then we work out all of that and distribute this through here. And then 3/2 is the same as 9/6. So I move that to the other side and combine, and this is our tangent line. Okay. Are there any questions? Okay, I will stop recording here, and I will repost these notes that are more up to date than the ones that were posted yesterday. The video will be posted sometime today in Canvas.